I was driving yesterday, stuck in that miserable gridlock on the 405, and I decided to dictate this long, rambling email to a colleague.
Oh, yeah?
And I was mumbling there was a police siren going by, and I'm pretty sure I was eating a bagel at the same time.
The ultimate test case.
Right. And yet I looked down at the screen, and the transcription was flawless. It even got the punctuation right. It just feels like magic. But it's starting to bug me that I don't know how it works.
It really is the ultimate black box of modern life, isn't it?
Yeah.
We just accept that the phone listens, it understands, and it types.
Yeah.
But if you actually strip away that user interface, what's happening underneath is this massive, high-stakes statistical battle.
A statistical battle. I like that. So today we are, tearing down the magic to find the math.
Let's do it.
We're doing a deep dive into a really foundational text in this field, Principles and Components of Statistical Speech Recognition, by Laurie Lamel and Jean-Luc Boivin.
And this paper is great because it refuses to anthropomorphize the computer. It doesn't pretend the machine has a brain or ears in the way we do.
No, it's pure engineering.
Exactly. It just treats speech recognition as a problem of maximizing probabilities.
And that's our mission today. We want to trace the journey of a spoken word from the vibrating air in my throat all the way to the digital text on the screen. And I want to get specific. No hand waving.
All right. The core concept you have to get is that the computer never actually knows what you said. It's not dealing in certainties at all.
It's dealing in likelihoods.
Just likelihoods.
So when I say hello, it's not hearing hello. It's calculating.
It is. The fundamental definition of the problem is mathematical. The goal is to find the most likely sequence of words. Let's call that Dirac, given the acoustic signal, which we'll call 6s.
Okay, so it's maximizing the probability of Dirac given $6.
That's the one. And it uses Bayes' theorem to break that down into two main components.
Okay.
First, the acoustic model, which asks, what is the probability that this specific sound wave corresponds to this word?
And the second?
The language model. And that asks, what is the probability that a human would actually string these particular words together in this order?
So it's balancing the raw sound against what? The context?
Precisely. It's this constant tug of war between what it thinks it heard and what it expects to hear.
All right, let's start at the very beginning then. The signal. My voice is an analog wave. It's continuous. Computers only speak binary. So step one has to be digitization.
Correct. This is what's called the front end. And the source material points out something critical here. The quality of that digitization defines the absolute ceiling of performance.
You can't analyze data you didn't capture in the first place.
Exactly. And they made a distinction between direct microphone input, like what we're using right now, and telephone speech.
Huge difference, right?
A huge difference.
Right.
A high-quality mic usually samples at 16 kilohertz. They give you this rich, detailed spectrum of sound. But the telephone network, it filters everything down to about 8 kilohertz.
Wow.
It literally just chops off the high and low frequencies to save bandwidth.
Which totally explains why automated phone menus are the absolute worst. I'm sorry, I didn't get that.
Yes.
It's because the system is effectively listening through a pillow.
That's a perfect analogy.
Yeah.
But okay, so once we have that digital signal, we hit a processing problem. A sentence is a long, complex stream of data. The computer can't swallow it whole.
It needs to chew it.
Right. So it chops it up.
Into what?
Into these tiny slices called frames. And we are talking about windows of time that are only like 10 to 20 milliseconds long.
That seems incredibly short. Why 10 milliseconds? Why not a full second?
Because sound is so dynamic. If you analyze a full second of speech, you might have 3 or 4 different phones in there. The cat sat. That's a total mess of frequencies.
Okay, that makes sense.
But if you zoom in to just 10 milliseconds, the human vocal tract is quasi-stationary.
Meaning it hasn't physically moved enough to change the sound yet?
You got it. It's taking a freeze frame, a snapshot where the sound is frozen in time. And usually it overlaps them. It'll take a 20 millisecond window, shift forward 10, take another, shift again.
So it's creating a flip book of my voice.
That's it. Exactly.
Oh, okay. So we have this flip book of raw audio frames. What is the computer looking for in those frames? Is it just measuring the frequency in hertz?
It is, but not linearly. And this is a really cool point in the reading for me. If you just measured frequency like a scientific instrument, linear hertz, you'd be wasting a ton of computing power.
Why? Because human hearing isn't linear.
Exactly. We are evolutionary marvels, but we're biased. We are really, really good at distinguishing low tones.
A tiger growling in the bushes.
Right, you need to hear that pitch change. But high frequencies, above 1,000 hertz or so, it all just starts to blur together for us.
So if the computer spent equal energy analyzing those high frequencies, it would be analyzing details that don't even matter for speech perception.
Correct. So engineers developed the Mel scale. It's a measurement scale that basically mimics the human ear. It stretches out the low frequencies so we can see the detail, and it compresses the high ones.
It's forcing the computer to hear like a human, so it focuses on the parts of the sound that actually carry linguistic meaning. That's brilliant.
It really is.
Yeah.
And from this Mel-scaled spectrum, the system extracts what are called cepstral parameters. You'll often see the acronym MFCC.
Which sounds like a delicious pasta dish, but I know it's math.
It stands for Mel frequency cepstral coefficients. Essentially, it's just a compact list of numbers that describes the shape of the sound in that 10 medes window.
But here's where I get stuck. A single frame is static. It's a photo. Speech is movement. If I say, wow, the sound is sliding, how does a static list of numbers capture that slide?
It doesn't. That's why the system adds delta parameters.
Deltas. Okay, that's calculus, isn't it? Rate of change.
It is. The system looks at the current frame and compares it to the previous frames to calculate the velocity, that's the delta, and the acceleration, the delta.
Whoa. So it's not just saying this sound is here, it's saying this sound is here, and it's moving toward a W sound at this specific speed.
Exactly. It captures the trajectory of the speech. And finally, before it passes this data on, it does one last bit of housekeeping called normalization.
Right, subtracting the mean.
Yeah. Imagine you are talking in a room with a loud air conditioner. That hum is present in every single frame. It's a constant value added to the signal.
So by calculating the average of the whole signal and subtracting it.
You mathematically delete the air conditioner.
That is so clever. It's active noise cancellation, but purely with math.
It is. So now we have processed the signal. We have a stream of feature vectors math representing the sound, its speed, and its acceleration with the noise removed. Now comes the hard part. What word is it?
And this is where we get into the acoustic models. The text says the industry standard, at least until very recently, was the hidden Markov model, or HM.
The HMM is the absolute workhorse.
I've seen HMMs described in other contexts, like for predicting stock markets or something. How does it work for speech?
Okay, think of a sound, let's say the P sound in Pat, not as a single point, but as a journey. You have the closure of the lips, the burst of air, and then the transition to the vowel.
Right.
And HMM models this as a chain of states, usually 3 to 5 states per sound, and they always move left to right.
So it's basically a timeline, state 1, then state 2, then state 3.
Exactly. And it calculates the probability of being in any given state and the probability of transitioning to the next one. But here is the design choice that makes or breaks the whole system. What are we modeling? Are we making an HMM for the word cat?
I mean, I would assume so. We want to recognize words.
But just think about the scale of that. English has hundreds of thousands of words. If you tried to build a separate, handcrafted mathematical model for every single word, you would need petabytes of training data.
Yeah.
You'd never finish.
Okay, yeah, that's wildly inefficient. So you break it down to the atoms.
Phones, the basic units of sound. English has, what, about 45 phones? It is infinitely more efficient to build rock-solid models for those 45 sounds and then just string them together like Lego bricks to make any word in the dictionary.
That makes sense. But wait a minute, Lego bricks are rigid. A red brick is always a red brick. But sounds aren't. A T sound is different depending on what I'm saying.
You've just hit on context. This is the co-articulation problem.
Right, so if I say T, my mouth is tight. If I say tool, my lips are already rounded for that oo sound before I even hit the T.
And the T itself is physically different.
Yeah.
Exactly. So a generic model for T would actually be pretty bad at recognizing both of those. To fix this, researchers developed context-dependent models, usually called triphones.
Triphones, so 3 sounds.
It looks at the phone in the middle, plus the phone on the left and the phone on the right. So you don't just model T, we model T preceded by silence and followed by E versus T preceded by silence and followed by ool.
Wow, so you go from 45 simple models to thousands.
Thousands. It totally explodes the complexity, but it's the only way to capture the reality of continuous speech.
And I'm guessing this also helps with the variability problem the text mentioned. I mean, my voice is different from yours. Men sound different from women.
A huge difference. The vocal tract length acts like a flute. A longer tube produces lower resonant frequencies. So generally, men have longer vocal tracts than women. The acoustic models have to account for this, often by, warping the frequency scale to normalize the speaker, or by training separate models for male and female voices.
Okay, so we've matched the sounds to these triphone models. We have a string of potential sounds. Now we need to figure out what words they make. We need a dictionary.
The lexical model. And this seems like it should be the easy part. Just upload the Oxford English Dictionary and you're done.
Hmm.
But Lamel and Guavain point out that this is actually a minefield.
Because nobody actually speaks like the dictionary. The example they gave was the word interest.
Right. How do you say it?
I say interest, 2 syllables.
And I might say interest, 3 syllables.
Yeah.
Now, if the system's dictionary is rigid and only expects that 3-syllable version, and you say interest, the alignment just breaks.
It's looking for a middle syllable that isn't there.
It's completely lost. So the dictionary needs multiple entries for the same word.
Pronunciation variance.
Yes. And it needs to handle lazy speech. Because we are all lazy speakers.
Oh, absolutely. I don't say going to, I say gonna.
Or did you, becoming dija.
DJ eat yet.
Exactly. If the lexical model doesn't map dija to the words did you, the whole sentence just falls apart. The system has to be street smart.
So we have the sounds, we have the potential words, but sound is messy. Sometimes I mumble. Sometimes a truck drives by. Sometimes the acoustic model just isn't sure. This is where the brain comes in, right? The language model.
This is the second half of our original equation, P's W dollars. The probability of the words sequence. This is pure statistics. It's the machine playing fill in the blank.
This is the n-gram concept.
Yes. An n-gram predicts the next word based on the previous n and above 1 words. So a trigram, the most common one, looks at the last 2 words to guess the third.
So if the computer hears New York, it looks at its database and says, okay, 80% chance the next word is city, 10% chance it's times, maybe 0.0001% chance it's pizza.
And crucially, it says there is effectively 0 chance the next word is ostrich.
New York ostrich, yeah, not a common phrase.
So let's say you mumbled, you said New York City, but the acoustic model thought you said New York City, like S-I-T-T-Y.
Okay.
The language model steps in and says, no, New York City makes no statistical sense. New York City does. I'm overwriting the years.
That's amazing. It uses probability to error correct the audio. But what happens if I do say New York ostrich? Maybe I'm at the zoo or something.
And that is the danger of these statistical models. If a sequence has a probability of 0, the map just collapses. The system literally cannot recognize it.
Just how does it prevent that?
It uses a back-off mechanism. If the specific trigram New York ostrich has never been seen in the training data, the system backs off to a big room. It asks, okay, forget New York. How often do we see the phrase York ostrich?
Probably still 0.
Right. So it backs off again to a unigram. How often do we just see the word ostrich? And that probability is low, but it's not 0. So the system multiplies it all together and says, okay, this is highly unlikely, but it's possible.
It's a safety net.
Exactly. It smooths out the data, so valid, but rare sentences don't just get rejected.
You know, before the final decoding, there was a section on text normalization that I found fascinating. We think of text as this clean thing, but for a machine learning to speak, text is a total mess.
It really is. Take the symbol $150.
$150.
But you don't say $150, you say $150.
Right. The word order flips. The symbol turns into a word at the end.
Exactly. So if you train the system on the raw text $150, it will never learn the word dollars. So before any training happens, you have to run these massive scripts to normalize all the text, convert numbers to words, expand abbreviations like doctor to doctor.
And strip out the garbage. The text mentioned garbage bracketing like HTML tags, tables, lists.
It's the janitorial work of AI. If you feed the system garbage text, you get a garbage language model. Simple as that.
Okay. We are at the finish line. We have the acoustic probabilities, the lexical options, and the language model context. Now the computer has to make a final decision. It has to output a sentence.
This is the decoding phase. And this is a search problem. You have to imagine a massive web of possibilities. Every 10 milliseconds, the path branches. Is it a P or a B? Is the word bit or pit? Is the next word bull or full?
It's a multiverse. There are millions, maybe billions of possible sentences.
And searching every single path in that multiverse is computationally impossible. You would take 10 minutes to decode a 10-second sentence.
Yeah.
So we use efficiency hacks. The big one is the Viterbi beam search.
I love that name. Beam search. Sounds like a sci-fi weapon.
It's more like a flashlight in a dark tunnel.
Yeah.
You only illuminate the path directly in front of you that looks promising.
Okay.
As the system moves through the time steps, it keeps a beam with a threshold. If a certain path is becoming too unlikely compared to the best path, it just cuts it off. It prunes it.
So it stops wasting power on New York ostrich so it can focus on New York City.
Aggressively. That's the key.
And the output isn't just one single sentence, is it? The text mentioned confusion networks.
Right. The system knows it might be wrong. So instead of just outputting text, it can generate a graph with confidence scores.
Right.
It might say, I am 90% sure the word is the, but there is a 10% chance it is a.
This is why, when you're dictating to your phone, you sometimes see the words flicker and change as you keep talking.
Exactly. That is the Viterbi search updating in real time. As you say more words, the language model gets more context, and it might realize that a previous word was actually something else, because the new path now has a higher total probability.
It's rewriting the past based on the future.
That is a very philosophical way to put it, but yes, that is exactly what the math is doing.
So looking at the big picture here, the source material outlines the history, and the progress is just wild. In 1992, they were happy with a 3% error rate on 1,000 words.
And that was read speech. In a quiet room. Very, very easy conditions.
Right. And now we are throwing podcasts, YouTube videos, Zoom calls at these things.
Found speech. That's the frontier. The error rates actually went up for a while because the data got so much messier, but the models got so much stronger. We moved from Gaussian mixtures to deep neural networks.
Which are basically just massive number-crunching engines.
Millions and millions of weights. And now the trend is end-to-end models. Trying to replace the acoustic model, the dictionary, and the language model with just one giant neural network. Audio in, text out.
That's very elegant, but does it work?
It worked incredibly well, but only if you have enough data. And that leads us to the final point in the paper, which they call the unsolved problem.
The data problem.
Specifically, the data problem for most languages. There are 7,000 spoken languages on Earth.
That is a staggering number. I had no idea it was that high.
But only about 15% of those even have a written form. And the vast majority of digital speech data, the stuff we use to train these massive models, it exists in maybe a dozen languages.
English, Mandarin, Spanish.
The usual suspects.
Yeah.
So strictly from a technical perspective, if you want to build a speech recognizer for a language with only 100,000 speakers and no written books, you're just stuck.
You hit a wall of data scarcity. You can't build a language model if you don't have text. You can't build an acoustic model if you don't have thousands of hours of transcribed audio.
It's a huge engineering bottleneck.
Yeah.
We have this amazing engine, but we don't have the fuel for 99% of the world's languages. And even within English, there's a data skew. The paper notes that unsupervised adaptation, where the phone learns your specific voice, it works much better if you already sound like the average speaker in the training set.
Because the starting point is closer to the destination.
Exactly. So if your accent or your dialect is an outlier in the data, the math has to work significantly harder to align your speech. It's just a reminder that these systems aren't magic. They are mirrors of the data we feed them.
That is a really powerful place to wrap up. Are we building systems that only listen well to people who already sound correct? Next time I shout at my phone to set a timer, I'm going to have a lot more respect for the meloscales, the triphones, and the beam search working in the background to figure out what I want.
It really is a marvel of applied mathematics.
Well, thank you so much for walking us through the mechanics of listening, and thank you all for listening to us.
My pleasure.
We'll catch you on the next Deep Dive.